Yeah.
And that way, is it are the Jasons really ending? I mean, they're the science article.
No, they're
terminated, but
not true. They're what happens is later, which is sort of Okay, well, let's get started. Today we have Andrew Houck from Princeton University to tell us about something which I think really quite wild stuff that will actually turn out to be real. I first heard about this some years ago about a field theory combining Cooper pairs in superconducting resonators with photons into coupled circuits, and then we go off from there. First, he presented sort of a clear notion of how that works, and I think we'll see some experimental consequences later. But this is really nice stuff, and something sort of involved your minds. He got his degree from Harvard, first with Charlie Marcus, and then Charlie took off for Copenhagen with Ike Schwang at MIT. And then went to work with Rob Schulkoff in Yale about Cooper pairs and the like. And then went to the place in Princeton where all quantum mechanics is done, which turns out to be the electrical engineering department for historical reasons. So I'm looking forward to your talk.
Great. Thanks for the introduction. If I get too loud, somebody hold your ears and I'll try and turn the volume of the mic down. I remember is it already too loud?
Yeah.
I remember I gave a talk in Spain about 6 or 7 years ago, and I took over the mic from like a series of European speakers, and I was like, "Hi, thanks for giving me this talk." And the entire audience winced, and the conference organizer ran up and said, "I'm sorry, we have to adjust the mic for American." And yeah, so anyway, okay, so I'm happy to talk about the work that our group has been doing on many-body quantum optics. This has been a decades-long effort which has spanned a number of different systems, and I will give you only a little bit of a flavor of this, and I really want to concentrate on actually a little bit more of the theoretical work we've been doing trying to figure out interesting new lattices. This is a quantum materials seminar, and so I'm hoping that we can actually have some discussions about maybe ways to realize some of these interesting lattices with actual real materials, and so there's something there. Okay, so this work has been done by a lot of people in my group over the years. The work I'm going to focus on today is really done by Alicia Kolar, my postdoc, who will be starting a faculty position at JQI in another month or two, and my senior student, Matthias Fitzpatrick, as well as Peter Sarnak in the math department. Okay, so the idea here, when you think about many-body quantum optics, right, if you think about many-body systems, very often you don't think of photons as a natural particle that you want to use if you want to introduce interactions and give rise to many-body states, right? Photons don't normally interact. They're kind of boring, right? I mean, if you just think about photons in a vacuum, you've got frequency, you've got intensity, you maybe got like a polarization or a phase, and that kind of describes all of light, and yeah, it's not so fun. And so the first thing we need to do if we want to think about doing something many-body-ish is to think about a way to get interactions. And the circuit we use to do that is circuit QED, which is the superconducting circuit equivalent of cavity QED. The idea here is you put one atom inside of an optical cavity, you have photons that live in the cavity, you have sort of two states in your atom, and this is quite a nice realization of the Jaynes-Cummings Hamiltonian. And in the world of superconducting quantum computing, which the other half of my group does, this is sort of the linchpin of actually doing everything that you possibly want to do, because if you put two atoms in this cavity, then you can have an atom that sits here and an atom that sits here, or a superconducting qubit. The photons will mediate an interaction between the qubits. In computer science language, you call this a gate. You string enough of these together and you suddenly have a computer, right? And so if you think about any of the superconducting quantum computing companies, they essentially use circuit QED as a way to mediate the interaction between two distant qubits, to do your 2-qubit gates and build up to a quantum computer. Now, This is, as I said, one major thrust of my group, but when I was starting my faculty position a decade now ago, it occurred to me that it's not so good to only do what everybody else is doing, and so we needed to think of something different to do so we could stand out and, I could not get fired and things like that, which are important goals of life. And so one thing that you can see if you look at this Hamiltonian is that it doesn't actually show a real preference for atoms as opposed to photons, right? This interaction term is perfectly symmetric. And so if you think about this, you could equally well imagine this not with 2 qubits and sort of photons mediating an interaction between the qubits, but as 1 qubit that mediates the interaction between photons, right? And if you get the coupling strength strong enough, you can get the effective photon-photon interactions that arise from this Hamiltonian to be a dominant energy scale in the problem. Now, in the world of circuit QED, we can make this interaction strength G enormously strong, right? Unlike real optical cavity QED, we have atoms that are many, many microns in size, and so when you displace charge to form your states, you have an incredibly large electric dipole moment. And we have 2 conductors that are used to make our cavity. We have a coplanar waveguide, which has a center pin and ground planes, which has different boundary conditions than sort of an open mirror cavity. In particular, while the length of this needs to be half wavelength long, the lateral dimensions can be arbitrarily small. And so the mode volume of a single photon is something like 10 to the minus 8 cubic wavelengths, which means the electric field is enormous, and so the electric field times the dipole moment is gigantic, and we can get incredibly far into the strong coupling regime. In terms of like cooperativity, for those of you who've done sort of optical cavity stuff, our cooperativities are like 10 to the 9 or 10 to the 10 or something. And so they're big. They're so big that we forget even talking about them because usually we're trying to like get our coupling smaller so that it's not quite so big. What that means is that if we add 1 photon to the cavity, even if the atoms are very, very far off resonance, it takes an enormously different energy to add a second photon to the cavity. If you have one of these things, you see photon blockade. And so you can think of this sort of nonlinearity that you get from the Jaynes-Cummings Hamiltonian as an effective photon-photon interaction. My favorite experiment that we did back when I was still finishing up in Rob's lab is this experiment here. So this is just looking at the vacuum-Rabi crossing with a qubit on resonance. And so these 2 peaks you see here are the 2 peaks of the vacuum-Rabi splitting. These are separated by plus or minus G. But if you drive the system more strongly, you can add 2, 3, 4, 5, 6 excitations into the system. Now, the degeneracy of the 1 photon qubit in the ground state and 0 photon qubit in the excited state, and the sort of 1 photon qubit in the excited state, 2 photon qubit in the ground state, and so on and so forth. These degeneracies are lifted with an extra square root of n that comes from the raising and lowering operators operating on the Fock states. And so if you pump from the ground state up in a 2 photon transition, you get peaks at plus or minus g over the square root of 2. A 3 photon transition gives you peaks at plus or minus g over the square root of 3, square root of 4, square root of 5, square root of 6. And so you can read out the square root of n of the raising and lowering operator sort of directly from the spectrum of this thing. And you can see that we have this just incredibly strong nonlinearity. And if you're thinking about this in terms of interactions, we can add 1 excitation to the system by pumping at this frequency, but we can't add more than 1 photon. And if we want to add a second excitation to the system, and we've added the first one here, we need to pump here, and then here, and then here. And so each additional excitation requires a little bit more energy. If the qubit is off resonance, the amount of extra energy is actually fixed. It really does look sort of Coulombic. If the qubit is on resonance, then the extra energy you add gets sort of smaller and smaller as you add more and more photons. And this gives you one knob that you can sort of adjust the effective interactions. Now, This is great. The very first experiment we did was to show photon blockade, where you shine light through and you see that it sort of comes through one photon at a time, and that's wonderful. But that's not really many-body physics. That's just showing you have a cavity with interactions. And so if you want to go from, a cavity with interactions into something that you might call many-body or at least multi-body physics, then you need more than one, right? And so what we've done over the last decade is think of all sorts of different ways to add more than one and think about lots of different ways to do many-body physics. And we've done sort of a whole host of experiments along these lines, starting with a Jaynes-Cummings dimer, where you have two cavities where you can think of each one as a lattice site, a 1D chain of 70 cavities where you can see something like a phase transition, some scanned probe techniques where you can image what's going on in these cavity arrays, some photonic bandgap materials where you can look at photonic bound states as a sort of dynamically tunable quantum simulator, and these massively multimodal cavities where you have G bigger than the mode spacing of a cavity, and you get these huge collective effects in this. This is a 70 centimeter long microwave cavity. So it's almost a full meter long. We have a version of this that's 2 meters, which is like really quite crazy. And so you can see these sort of, yeah.
So how big? I can't read the.
So this entire chip, this is 10 millimeters. So this is sort of an inch by an inch chip with a an almost a meter long cavity coiled up inside, and we put one atom right there at one end of the cavity, and we get strong coupling to every mode of this cavity. And if you drive the system, what you actually see is this sort of really interesting collective excitation of all the different modes, which sort of phase lock to each other and create an incredibly narrow emission line that's sort of 100 times narrower than any of the line widths in the problem. And so you see this sort of collective behavior in this system. Today, what I want to focus on is sort of this square here. And so what I'm mostly going to talk about today is sort of trying to use these things to look at hyperbolic lattices and to think about what are all the interesting kinds of lattices that we can make and what kinds of properties that we can get out of them that are particularly interesting. The reason we focus on this is because superconducting cavities and qubits give us this sort of really special property that allow us to make these kinds of lattices, which are much harder to do in sort of typical cold atom quantum simulators. And so it's a place where we have something that we can do that's a lot harder in other physical systems. And so it's sort of an area that's rich for scientific exploration. Okay, so just to give you an overview of some of the types of things we've done in the past, so very quickly, the very first experiment we did when we wanted to go from one cavity up to many-body physics was to make two cavities, and right, so that's at least multi-body physics. And the idea here is that we have two cavities. Photons can live in either cavity, the left or the right. If you put a large number of photons in one cavity, and there are no interactions, then they will sort of oscillate back and forth between the two cavities, since they will be very much delocalized. As you turn up the strength of interactions between these photons, the interactions sort of create a localization effect, and so they want to stay in one cavity. And so as a function of the interaction strength compared to this sort of hopping strength, you can see that the photons either stay in one cavity or delocalize between the two cavities. And so if we start with some number of photons, you can see that they sort of oscillate, and when we turn off the interactions below some critical value, they sort of suddenly stop in one cavity. And so you can sort of map out a dynamical phase diagram like that. In a large disordered 1D array, you can see some bistability and long switching times effects that are sort of hallmarks of the kind of phase transition you expect in these sort of disordered systems. You can see this bistability with switching times that approach 10 seconds in a system where, in the steady state of a system where no individual thing lasts longer than 100 microseconds. And so this sort of critical slowing down as you approach this sort of sort of threshold point is actually quite interesting. But today, as I said, we want to sort of push this to talk about new lattices and 2D lattices and not some of the old work. And that's really what the focus of the talk is going to be. So this is a lattice. This is the very first 2D lattice we ever made, and it's now 6 or 7 years old, which makes me feel old. And if you look at it, you can see a few interesting things. So one, there's a lot of these squiggly lines, and what each of those squiggly lines is a. Oh, I don't have the squiggly line zoomed in. So each of these sort of squiggly lines is one cavity. So sort of between this dot and that dot is one cavity, between this dot and that dot is one cavity. The length of the cavity determines its frequency, but in superconducting systems, you know, the microwaves just follow your wires. You're allowed to bend it around and turn it however you want, as long as you don't bend it sort of exceptionally tightly. And the entire structure of the lattice, the hopping, is determined only at the very endpoints by the capacitive coupling between one cavity and its neighboring cavity. So in this system, we've made an array of about 200 cavities. The endpoints come together in this sort of three-way structure, which gives equal capacitance between neighboring cavities. This capacitance leads to a hopping term that allows photons in one cavity to hop to a neighboring cavity, and this realizes essentially a tight binding solid where you have some on-site energy for the number of photons at each lattice site and the ability to hop between nearest neighbors. Now, for a while, we thought the sort of most exciting thing that we can do with these CPW, with these superconducting lattices that are sort of harder in atomic systems is the fact that this is a very fundamentally non-equilibrium system, right? Our particles are photons. Photons, in the end, don't stick around forever. Particle number isn't conserved. And so we're often looking at sort of steady state or dynamics of systems. And so they're very good at non-equilibrium quantum simulation. But about 2 years ago, the thing that we really started to focus on was the fact that our resonators are deformable, right? Our resonators are long and skinny. The frequency of a resonator depends only on the length, and the coupling depends only on the ends, and so we can bend them. And so the three resonators you see here all have the same length from end to end, but they all have very different shapes. Now, this seems almost like a trivial thing, but when you're trying to build lattices, this is an incredibly powerful tool because it allows you to decouple distance from sort of hopping rates. And so if you want to build a lattice with a uniform hopping rate across your lattice, but you don't want your lattice sites equally spaced, this suddenly allows you to do that, and that opens up a whole new world of lattices, right? And so if you think about a real actual material, right, and you sort of imagine these red blobs are your atoms, you know, this is a nice thing where every atom can hop to its nearest neighbor with the same rate because the wave functions overlap the same amount. If you disorder this lattice, some points are closer together and some are farther apart, and if this were a real material, the points that are closer together would have high hopping rates, and the points that were further apart would have low hopping rates. But what we can do is we can take this sort of physically disordered lattice where distances are different and create a uniform hopping material. And what that means is all of the properties of our systems are entirely governed not by the physical layout, but by the graph. The graph defines everything. And so if we start to look into graph theory, then that can really inform the types of things that we can build in this lattice. And so we are going to take a very long detour into the world of graph theory and some pure math because that's what we decided would be fun to do. And it's been fun. So okay, we're going there. Okay, the first thing you need to point out is that if you look at this system, unless you are more clever than me or have heard me talk before, you will probably guess the lattice wrong, right? So if you look at this, I've sort of straightened out all of my lattice sites so that they're not squiggly anymore, so you can see effectively what we're drawing is this tiling of hexagons. And what lattice is this? So it looks like a honeycomb lattice. The layout looks like a honeycomb lattice, but you have to remember that the key trick here is that each of my lattice sites is this sort of long, skinny thing, and each of my points is where the hopping happens. So although the layout has this appearance, the actual lattice looks like this, where I have a lattice site, which is now a point at the center of each resonator, and the hopping is determined at the endpoints. And so you can imagine I can get this lattice from this lattice by putting a point in the middle of every edge and drawing a connection to every other edge where they share an endpoint. In mathematics, this is called taking the line graph. and we will denote this original sort of layout graph that we draw by x, and the line graph by L of x. And so what we draw, the things that we physically draw, are layouts. The things that they realize are line graphs. And so a lot of what we're going to be doing is studying properties of these line graphs. An important thing to note is that this turns out to be the simplest 2D lattice we can make with uniform hopping, because we bring 3 resonators together. That's the sort of easiest structure we can make, where we have uniform hopping between all the resonators, which means the easiest lattice we can actually realize in our system, the easiest 2D lattice, is the Kagame lattice, which is what this guy is. Okay, so from there we decided, well, if we can build all sorts of things, let's try and build the sort of craziest thing that requires deformation, and that was really to start looking into curve space. And one of the main motivations for this starting out was that curve space is actually really interesting, right? We have all these lattice simulators that let us sort of have a nice lab testbed for quantum mechanics. We know that curve space exists in gravitational systems. We know that quantum mechanics and gravity don't mix too well, and so if we can start looking at lattices in curve space, maybe we can start getting some insight into sort of quantum and gravity. I say quantum and gravity and not quantum gravity because right now the curvature in the metric R space is entirely encoded by the layout, which is fixed. And in order to really look at quantum gravity, you need the system to actually be able to influence the layout, but there are ways that we might be able to do that in the future, and so that's something we're thinking about. So if you think about curved systems, there's sort of 2 signs of curvature. There's positive curvature, which is the spherical thing. That's the thing that's easier to picture, right? That's sort of the surface of a buckyball, the surface of a soccer ball. The polygons here are sort of puffy, if you want to think about that, and the space in some ways is smaller than flat space, and parallel lines importantly converge. It's pretty easy to picture positive curvature. You can draw a surface that represents positive curvature in 3D space, right? So you have a ball, it's a ball. For negative curvature, actually, there's no embedding of a 2D hyperbolic plane in 3D space. So it's actually quite hard to imagine in your mind what negative curvature space looks like, and it's actually sort of the more important and more interesting space. And so this is really where we're going. In hyperbolic space, parallel lines diverge. The polygons are skinny, and the space is in many ways bigger than flat space. Okay. So if you just try and think about now drawing structures, right? So we're gonna try and take what we did with the honeycomb / Kagame lattice and start tiling other interesting kinds of lattices, right? You can imagine we want 3 things to come together. So probably the easiest thing to do is to tile other polygons, right? So we could try imagine tiling pentagons, right? And in Euclidean space, you can't tile pentagons. They're not puffy, and so there's this sort of gap that you get that you can't deal with. But if you're willing to change distance, then you can actually tile pentagons, but you can't do it in a way that preserves the distance of each side. And so you have to sort of deform your 2D space in order to make the tiling possible. And similarly, if you want to do hyperbolic space, if you try and tile heptagons, you get an overlap between these polygons. And so you can't actually make that tiling work unless you again deform distance and make things get smaller as you go out from the center of this tiling. But as long as you're willing to make distance something that is not preserved, then you can go about and sort of make this projection into a 2D plane. Now, the problem, if you're doing with real materials, is that as you do this, well, you know, things get closer and closer and closer together, which means the hopping rates get larger and larger and larger as you go out, and suddenly this doesn't realize this sort of uniform hopping material, but we can just sort of squiggle things, you know, and as things get closer together, we squiggle them more, and as things get further apart, we like stretch them out, and we can use the deformability of our resonators to allow us to do these sort of weird projections. And so suddenly we have a system that allows us to build these lattices that are essentially curved space lattices on a flat chip, which is far easier than doing lithography on like a spherical chip or something, right? That would not be so pleasant. And so, yeah.
Yeah, so I wonder, just thinking about the Jackson version of this, you're saying that if you have a wire that has a magnetic field going around it in a spatial pattern, if you start putting zags where they're going in the opposite direction, it kills the inductance and things like that. Does that all not matter because you're not right?
Yeah, so there's ground planes in between, and you have to be a little careful about your bend radiuses. And it turns out that like the length of the wire being absolutely the only thing that matters is like slightly off. If you put more bends in them, then the frequency changes slightly, and so we actually. Every resonator in these lattices is not identical. It is sort of an artisanal 2D lattice where each latticite is handcrafted and trimmed to be just right. And so my graduate students cooled down sort of each individual shape we wanted to use separately and measured its frequency and the disorder in its frequency and adjusted them to try and make it really, really, really right. But that's an effect that you need to do to get from sort of 0.1% disorder to 0.01% disorder or something. That's sort of that extra sort of factor of 10 in repeatability. Okay, so the next thing we want to do is we're going to start, okay, well, what do the band structure of these things look like, right? I mean, this is the band structure of the Kagame lattice. It's got these two bands. It's a great lattice, actually. And it has one feature that we really, really like, which is something that we're going to focus on a lot in this talk, which is this flat band, right? So it's got these two bands. It's got Dirac cones. It's got three bands, but it's got two curved bands. It's got Dirac cones. It's got a flat band. For us, the Kagame flat band sits at the bottom because T is negative. It just depends on the way the electric fields come together. So for those of you who've seen Kagame lattices upside down from this, that's why it's upside down. The thing that we don't love about this is that the flat band touches the other bands, and we really want spectrally isolated flat bands in order to do interesting physics. And so that's something we'll talk about a lot later. Flat bands are particularly exciting for us because if we want to look for the emergence of many-body physics, we want to turn on interactions. And life is far easier if we start with weak interactions, but we still want them to be a dominant energy scale in the problem. If we start with a flat band, then essentially arbitrarily small interactions wind up still being a dominant energy scale in the problem, and you can give rise to many-body physics. And so flat bands are a particularly powerful starting place to do many-body physics, but only if they're spectrally isolated, because otherwise your interactions just mix you with the other bands and it gets less exciting. Okay, so problem number one, and problem number one for anybody in the room who's a theoretician, is actually the most important open challenge we have, and one that is really important to us as physicists, but even more important to us, it is really important to the pure mathematics community, which particularly cares about this, and that is how do you do block wave theory, right? So hyperbolic geometry is not commutative, so parallel lines diverge, translations do not commute anymore. And so if you think about trying to draw a band structure, well, band structure sort of relies on you having a Bravais lattice and block theory, but this non-commutativity makes your sort of typical approach to block theory no longer work. And so we cannot draw band structures for any of our non-Euclidean geometries. The tools we have at our disposal, which are quite powerful, are graph theory to help us with the analytics, and brute force tight binding numerics to help us figure out what the heck is actually going on in some of these finite systems. We have a pretty good reason to believe, based on the brute force numerics, that there is, in fact, an underlying band structure, right? We see features in our tight binding numerics that you would point to and say, like, you know, if I showed you a density of states which you get from the numerics, you would look at my density of states and you'd be like, that thing there is a Dirac cone, and like that thing there is a Van Hove singularity, and you would look at it and you would definitely feel like there ought to be an underlying band structure, to the point that our mathematician collaborators are quite convinced that there is something to do here, we just don't know how to do it. In the math community, understanding the structure of these hyperbolic lattices is closely related to the solution to the Riemann zeta function and proving the Riemann hypothesis. And so there's a huge interest in the math community in trying to understand how this stuff works. Okay. For our point of view, I'm going to show you a lot of plots that are either density of states or pictures that look like this. This is just sort of listing from brute force numerics, diagonalizing a big old matrix. What are the eigenenergies of this, assuming T is equal to 1? And so for the Kagame lattice, you will see sort of some continuous range of eigenvalues and a flat band here, which corresponds to some highly degenerate eigenvalues that sit at -2. And so when we do numerics, we can sort of build more and more shells of this by adding a ring of heptagons around the perimeter. And as you do that, you see that, that these sort of continuous bands get more and more densely filled in until it's essentially a completely continuous thing where you have a flat band and some continuum of objects. But if you do this for a tiling of heptagons instead of hexagons, so if you do this for the heptagonal Kagame lattice, instead of the normal Euclidean Kagame lattice, you will note one thing never actually gets filled in here at the bottom, and that is that the flat band is suddenly gapped from the rest of the system. Yes?
What do you mean by band? There's no momentum, right? So
I mean, you can locally define momentum, but I would say you can locally define momentum, and you can prove analytically that there are finite many continuous intervals from -2 to 4 in these lattices that will have finite density of states. And so you can sort of write this in terms of saying something about the density of states. But you're right. We don't know what the underlying band structure is. So what we can say is about the hyperbolic case is that there's a highly degenerate set of eigenvalues at -2 that are localized and highly degenerate. And so those would be what you would call a flat band. So a highly degenerate set of localized states with overlapping support and identical eigenvalues. So that's what you would call a flat band, and it is gapped from all of the other states in the system.
So different states that have that same eigenvalue are just localized in different places? And just like
Yeah. So and I'll show you what they are in a second, right? So those are gapped. And we started to ask, is this gap coming because of the curvature? What is this gap coming from? And so you can do numerics for the normal Kagame lattice, this hexagonal Kagame, which has no gap. The heptagonal Kagame has a gap. The octagonal one has no gap. The nonagonal Kagame has a gap. And so it certainly seems like it depends on the whether we're dealing with something that is even or odd. And you can actually enumerate what these flat band states are, or what these localized states are, right? So for the Kagame state, they are modes that have equal weight around one hexagon, where you alternate the sign from positive to negative. And if you think about this, if you think about having this state and then thinking about what the hopping terms in the Hamiltonian do, well, that tries to make sort of these two states hop to this lattice point here, but you get a positive contribution from this and a negative contribution from that, which destructively interferes. So you can't hop onto this lattice site. But similarly, you can't hop onto this lattice site, or this lattice site, or this lattice site, or this lattice site. And so you wind up having sort of this destructive interference, which prevents you from hopping off this lattice site. That gives rise to your localization. And so the flat band states, and here it really is a band, in the Kagame lattice are these sort of alternating signs around the hexagon. If you try and do that for the heptagonal Kagame lattice, where you have a gap, you can't actually alternate signs around a heptagon, right? Because you wind up essentially with frustration. You can go around two heptagons, and so the sort of degenerate states here are these sort of alternating signs with an even number of lattice-site closed loop, which goes around a pair of heptagons. And then in the octagons, it's again going around one loop, and the nonagons, it's going around two loops. And this starts to give you a hint as to where the gap comes from, and we will use this to make lots of interesting lattices in a little bit. Yeah?
So how do you implement the boundary?
So you can do a few things, and it's a really good question and a very important one for these hyperbolic. So in all of the numerics you see here, we're doing a hard wall boundary condition, so we're just truncating the lattice site as you see. We're truncating the lattice site after some finite number of shells. So it's a hard stop. You can try and remove at least some of the boundary condition effects by doing a randomization of the boundary. So if you allow every boundary point to be randomly coupled to another boundary point, and you sort of randomize that, and then you sort of average over that, you can get rid of some of the boundary effects. boundaries are a real problem thinking about the numerics in the Kagame lattice, because in hyperbolic space, the boundary is always a finite fraction of your total volume, right? And so as you make these, normally if you think about a sort of finite size numerics, if you make the system larger, the boundary effects become less and less important. Here, the boundary effects become equally important, and so you have to think about how to deal with them a little bit carefully. But what the boundary effect does, and we can show this in a little bit, is that it actually makes the gap look smaller than it is. So a lot of the edge states that live, we actually do get edge states. The edge states are basically in the gap of what you would get for the infinite hyperbolic Kagame lattices. Okay. So just to show that we can build these things, because we really want, yeah.
I'm still trying to get some pictorial way of seeing it. Yeah, that one and all the way to the left. And so you say it likes to localize in that hexagon.
Yeah.
So I like that.
Well,
but then where's the next hexagon over the next localized?
So it's every hexagon. So it's here, 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 here.
And then they touch.
And then they touch, and the touching is actually important. So the touching is good because you know, it doesn't affect the localization. You can count these as localized, but when you turn on interactions, the fact that these don't have disjoint support means that the interactions are going to sort of mix them and give rise to your interesting many-body states, right? If you had interaction, you know, I could easily make you know, a set of localized states by having like a hexagon here, which is completely uncoupled from a hexagon here, and just like you know, isolate these, and then you get localized states because they're just like puddles that don't couple. And what's exciting about the flat bands is that they have overlapping support, and so they're not totally disjoint, and yet still localized. Okay. So we can make these, and we're going to make many different kinds of lattices, but we can make these things just to test disorder. So we made this guy. It's a two-shell construction. It operates at 16 gigahertz. We have to operate at the full wave mode of these resonators for these kinds of experiments, because if you're at the half wave mode, then you get a second kind of frustration, which is that the endpoints of your cavity have different sign, and that causes all kinds of other weirdness to happen. And when you do this, you can get a transmission spectrum, which you see in blue. The red is a set of theory curves that you can generate for what you would expect the transmission spectrum to look like if you had 0.01% disorder in cavity frequencies. And so this is sort of sampling over what the disorder spectrum looks like. And there's for these kinds of lattice experiments, this is remarkably good consistency for us. There's a little bit of discrepancy in the amplitudes here, but very much you're matching peaks and dips to peaks and dips, which is quite good. And it gives us, sort of doing this kind of matchup, gives us an idea of exactly how much cavity disorder we get, which gives us an idea of whether or not we will be able to use these isolated flat bands to do interesting many-body physics or not. And if you look at this amount of disorder, it is right at the edge of where you might say we could do interesting physics, but not quite good enough. And so we really started to think about, can we get a bigger gap to our flat band, which would just make the disorder way, way, way easier to deal with. And so that started getting us thinking about where the disorder where these flat bands are actually coming from and where the gaps are coming from. And that sort of is what launched us really into this very mathematical direction. And so the flat bands, it turns out, come from the fact, this sort of curious fact that I pointed out early on in the talk when I sort of drew this honeycomb lattice, and I said, what is this thing? And it wasn't actually graphene, it was the Kagame lattice. And so for any lattice we draw, we are actually realizing the line graph of that lattice. And we can do graphene, which is a Euclidean lattice. We can do this heptagon Kagame lattice here. We can make trees, and you can also do this for the square lattice. Now, for the Euclidean ones of these, we can calculate a band structure, right? So for the graphene and the square lattice, we can calculate a band structure. And if you look at the band structure of the square lattice, you get these sort of sinusoidal bands. And if you look that go from -4 to 4, which is what we expect, this is in units of t. It goes from -4 to 4 because each lattice site here has 4 nearest neighbors. And so the entire spectrum should be from -4 to 4 if it has 4 nearest neighbors, -3 to 3 if you have 3 nearest neighbors. So the coordination number determines the range of the density of states. And if you look what happens when we take the line graph and look at the band structure of the line graph, it looks identical, except here it is shifted up by 2, and there's a flat band at -2. Here it's shifted up by 1, and there's a flat band at -2. So when you look at the band structure of these line graphs, it looks very much like the band structure of the underlying lattice, but you've got an additional flat band that appears. And so this is sort of where we started looking, because this would give you a prescription both for figuring out when you get a gap and for figuring out how you get flat bands, right? And it really does look like line graphs just give you a flat band. Okay, so you can start doing this by defining Hamiltonian. So we can define a Hamiltonian H sub x, which is the Hamiltonian for the tight binding layout of the underlying lattice, and H sub s or H of L of x, depending on exactly what we're writing, can be the line graph of the Hamiltonian on the line graph. This is really only looking at the hopping part of the Hamiltonian. We're sort of subtracting off the on-site energy. And we can describe the entire graph with an incidence matrix that tells us how the set of edges is connected to the set of vertices. And this is something that essentially allows us to map from our graph to our layout graph. And so this is an incidence operator, and it gives us, you can think of the rows as the edges and the columns as the vertices, and you have a 1 here if the edge and vertex are incident, and a 0 otherwise. And so it's a matrix that encodes whether or not your edge touches a particular lattice site. Okay. Now, if you think about what this does, you can think about this as a way of traversing a graph. So suppose we start with a state on our graph, which is just this big orange ball here. So we start at 1 lattice site, and we multiply this state by our incidence operator. What it does is it gives us a superposition of all of the edges that are incident on this vertex, which are these 3 edges. If we then multiply this by m dagger, it will give a superposition of all of the vertices which are incident on these edges. So each of the endpoints of these 3 edges, which will give us these 3 points plus the original lattice site 3 times, because it will come once from each of the 3 edges. And so if we want to write that in terms of a matrix language, we can say that m dagger m is equal to our Hamiltonian, right, because we've taken our original site and we've hopped to all the nearest neighbors, plus a diagonal matrix, which is the degree of each vertex. And if every vertex in the graph has the same number of nearest neighbors, this is just the identity matrix where times the coordination number of the lattice. And so here it would be 3i. We can similarly start from a single edge and think about what this incidence matrix does. So if we multiply this by m dagger, we go to the 2 vertices that are adjacent to this edge, and that gives us these two vertices. And then if we multiply m dagger, that brings us to the edges that are incident on these vertices, which give us the 4 edges here, and then back to our original edge 2 times. Now, if you think about the line graph of this graph, these edges are lattice sites. And so what you've gotten is all of the nearest neighbors of this original edge plus the original thing times 2, because it had 2 endpoints. And so you get 2i plus the Hamiltonian of the line graph. And now the big exciting thing is that there's a correspondence between the eigenvalues of m dagger m and the eigenvalues of m dagger. That is, if you have a state that is an eigenvector of m dagger m, there's a corresponding eigenvector of m dagger that has exactly the same energy. And so these things share eigenvalues. And so there's if you abuse notation slightly, for the shared set of eigenvectors, equivalent, and if this matrix is in fact, if the graph is D-regular, so if everybody has an equal number of lattices, then this just gives you D for every latticite, this gives you 2 for every latticite, and it relates the energies of the original lattice to the energies of the line graph. And in particular, the energies of the line graph are D minus 2 plus the original energies. And there's a bunch of states that are in the kernel of this operator here, and those all have energy minus 2, and that gives rise to your flat band. So all the things that are not in the kernel have a correspondence between the eigenenergies, and then you pick up a whole bunch of things that are in the kernel, which are all at minus 2 that give rise to your flat band. What this means is that the energies of your line graph for a 3 regular graph are just all of your original energies shifted up by 1 with a flat band that appears at minus 2. And so if you look at density of states, which we saw before, for the original graphene lattice, the density of states stretches from minus 3 to 3. The density of states of the line graph stretches from minus 2 to 4. And the band structure in this part of the density of states is the same, and you get a line graph at minus 2. For the square lattice, it shifts up by 2 because the degree is 4. For the tree, for a 3 regular tree, it shifts up by 1. And you get a flat band at minus 2. And for the heptagonal Kagame lattice, it shifts up by 1, and you get a flat band at minus 2. And the thing that is really interesting is now we have a criteria for when you get a gapped flat band, right? So you always get a flat band when you take the line graph of a regular graph, but you get a gap when the minimum eigenvalue is not minus D. So if you start with a D-regular graph, note that here the minimum eigenvalue is minus 3. That's not going to be gapped, because it just shifts up by 1. Here, the minimum eigenvalue is not minus 3, and so you wind up getting a gap. And so whether or not, what the minimum eigenvalue is entirely tells you whether or not you have a gap, and it also tells you the size of the gap. And so what you can do is you can then start to imagine ways that you can figure out when there's a minimum eigenvalue that is D or not D, and it turns out that it is entirely related to the bipartiteness of the underlying layout graph. So if the graph is a 3 regular graph and it is bipartite, there will always be states that have energy minus 3. If the graph is non-bipartite, there can never be states that have energy minus 3. And so you get a gapped flat band or a not gapped flat band when you take the line graph of something that is not bipartite or bipartite. And so from there, you can start to actually draw Euclidean lattices that are 3 regular and have this non-bipartite property, which have basically only odd-sided polygons. And in particular, you can imagine a graph that is rippled in terms of curvature, where you put in rows of heptagons, which are negatively curved, and rows of pentagons, which have positive curvature. And if you alternate these, then you can get a graph that is perfectly Euclidean and perfectly non-bipartite and 3 regular. And so the band structure gives you quite a large gap at minus 2. This is great. You can then start to think about crazy things about how large can a gap be. The largest minimum eigenvalue of any regular graph is minus D plus 1. So the largest gap you can ever get is 1. And so we started thinking about whether we could find graphs that realize that. And so now we started playing around and proving all sorts of theorems about what different operations you can do to a graph do. And in particular, the one we found particularly interesting was the subdivision. So if you take a graph and on every edge you insert an extra latticite in the middle of the edge, then the band structure of the subdivided graph, which is now a 3-2 biregular graph, basically takes your original band structure and makes 2 copies of it at square root of e plus 3. And so here's the positive square root of e plus 3, here's the negative square root of e plus 3, and it introduces a band at 0. If you take the line graph of this 3-2 biregular graph, you get this set of bands, which give you things that relate to the underlying band structure of the layout graph. And importantly, the line graph of a subdivision graph is a 3 regular graph where the minimum eigenvalue is always minus 2, which means that the line graph of the subdivision of any regular graph will always be a graph which itself gives rise to a maximally gapped flat band if you take the line graph of this. And in particular, if you take the line graph of this, you see you get a flat band at -2, which is maximally gapped from everything else. And so this is a constructive way of building different lattices that give you flat bands that are maximally separated, provably maximally separated from all of the other bands in the system. And this gap is enormous and allows us to do all kinds of exciting things. There's one more thing I want to say, which is, you also have this flat band at 0, and you can figure out ways to make this flat band at 0 maximally gapped. And there is, in sort of going through all of this, we found one lattice so far which gets rid of this property where we need non-equal spacing. And we have this lattice here now that actually has equal spacing between all lattice sites, a gapped flat band at 0 that is maximally gapped and can be sort of laid out in a Euclidean geometry with equal spacing between everything. And so if you have an ability to think about real optical lattices or real materials, this is something that we could actually start to think about trying to lay out in a real system and get a flat band that is massively gapped from everything else.
Again, I'm trying to get some visualization. Suppose you were going to make a Wigner crystal out of this flat band, like you're going to put some electrons in there that they have some charge with. They repel each other, so that it's flat, so that when they're apart, they're pretty far away from each other. Where would they sit?
So if you turn on the slide, okay, so this is a great question. So now basically you're saying now we have particles where we know where they would live if you don't turn on interactions, and now you turn on interactions, and what many-body states emerge?
No, just suppose it's a very weak interaction. Then they'll go snuggle into some little cubby hole.
Yeah.
And then if I knew where the cubby holes were, then I could come up with some freshman level model of the interaction.
Sort of, though I would say if you have truly flat bands, even if you have incredibly weak interactions, that's going to give rise to something that's many-body. Right? And so even if you try and turn on weak interactions, you actually suddenly have to do real many-body physics to figure out what will happen in these things. We have engaged with a number of many-body theorists who are thinking about this. We invite many more, but it's a really good question, and we don't know the answer of what states emerge from these kinds of crazy lattices. What we know is that this is sort of a promising venue for making, weakly interacting systems sort of have really interesting emergent behavior.
But in this twisted graphene, which is what people are trying to figure out, it goes insulator and then superconducting when it's half filled. And they tell me at the moiré pattern where it goes yellow and where they're lined up like this, that's where the electrons sit. Is there some sense to that?
I mean, so I could speculate. I mean, we know what there in these kinds of lattices where there's a complicated unit cell, there's sort of a handful of different flavors of where the flat bands tend to be, and we have some guesses as to which ones would probably wind up being dominant, but it's all a bit speculative right now because it's actually a really hard numerics problem. Okay. So I am really running low on time, so I will sort of show a few quick things. So one, here's the band structure of our octagonal graphene paper. The resolution on this one, I keep meaning to switch this figure out because the resolution of this was back before we did the fancy numerics. The problem with doing high numbers of lattice sites in the numerics is like as you add more and more shells, like these things grow exponentially. But if you sort of zoom in at this middle point, there's a perfectly linear dispersion to 0 and back out here, and there's a very sharp cusp here, and there are sort of these features here that really sort of look like much more structured than any mathematician had predicted you would get for these hyperbolic lattices. And so this really implies that there's some actual underlying structure that we haven't yet figured out how to get access to, and we're really trying to do that from a theory perspective. Experimentally, we've started making these things not out of purely linear systems, which is what I showed you for the hyperbolic data, and not putting qubits in each one to get incredibly strong interactions, but out of sort of materials like niobium tinitride, where you have a high kinetic inductance. This allows you to get weak interactions that are more like a nonlinear wave equation by adjusting the power of the system. And so it allows you to sort of in situ tune weak interactions and look for what emerges. And when you do that, you actually see really interesting behavior already. And we've done a lot more than this, but it's sort of still a bit preliminary. If you drive it weakly, what you get is you get sort of a single point in the IQ plane, which is sort of transmission at a single frequency. As you drive it a little harder, you get these sort of closed curves in the IQ plane, which give rise to sort of comb-like behavior. The density of the comb actually increases as you drive it harder, and at some critical driving power, the thing actually goes fully chaotic. And if you measure Lyapunov exponents of it, you can actually prove that it goes from a stable system to a fully chaotic system. And so there really is, even in the very weakly nonlinear system in these sort of arrays, you actually see some interesting physics already arising. And I'm happy to talk a little bit more about this, but I wanted to focus today mostly on the sort of lattices that we can do, so that to show you that we actually have some really interesting tools, both in terms of what we can fabricate, and we now have a very long mathematical physics paper that talks about all the sort of underlying band structures and sort of how you can do interacting photons in curved space. So thanks for your attention, and yeah, it was fun.